Okay, so we've talked about assessing maximal velocity. Now let's talk about assessing acceleration, the other component of linear speed or maximal sprinting speed. So you can model acceleration of splits in like a 5, 10, 15, 20 would generally be the consensus for field sports, or up to 30 meters in the track, as mentioned before, from those definitions from Hess. One of the cool things that have come out recently is from Sam Zeno and JB Morin, are the two people that have been promoted, is this force velocity profile over 30 meters from a 3 or 4 point acceleration. I like doing it with a 4 point acceleration, but you can use a 3 point as well, depending on what athletes you're working with. And what it gives you a number of different values. So it'll give you F0, which is force at zero velocity. It'll give you V0, which is velocity at zero force. It'll give you power. It'll give you the DRF, which is the decline in the rate of horizontal to vertical force. So obviously you want to have that lower if you want to accelerate faster. The RF max is the ratio of force or ratio of horizontal force compared to vertical force. The higher is better in acceleration because you want to be moving horizontally down the track more than what you want to be moving up and down the track. And then we'll get this force velocity slope, and I'll show you what that looks like. You can pick this up with radars or splits. 5, 10, 20, 30 meters are splits that you would probably need minimum. You can do it with a 10, 20, 30, like 0, 10, 20, 30. You need to have the timing trigger on the person's hand because it's based off when the person lifts off their hand off the floor, or rather when they break a light or break a gate in acceleration. It's based on when they actually lift off their hand and start moving forward. That's when the acceleration will start. And that's where all the computations and calculations are done from. You also have an option for in situ acceleration. This is based on GPS. Again, JB Moran's put that out. Really good option if you work with GPS day in, day out, you're a field sport, professional field sport, you have access to GPS. I'd 100% recommend using the in situ acceleration variations there. You could also pick that up from a 30-meter acceleration, though, from pulling apart the GPS data you get as well. Is the other option, and just doing it in the traditional way instead of using radars or splits, or a combination of timing gates and GPS would be probably my ideal. One of the things you can do, and this is what I've done for field sport athletes in the past, is I just use that last 10 meters of the 30-meter test I'm going to do for my flying 10. We did mention that most field sport athletes, at least in the research on the NFL Combine, will probably finish accelerating by the 20-meter mark. So that one thing I do is we set up as both tests at the same time. You have your force velocity profile and dig all the data out from what we get from Sam Zeno and Marin. And then I'll also have that flying 10 as the last segment that I'll pull out that time, and then it'll give me projections for what an athlete should be able to do in that flying 10. Let's have a look at what this might look like. So this is an acceleration with a younger, I think he's about 18 years old when I was working with him, younger athlete, very, very good 200-meter runner. And we're just looking at acceleration. It'll be off. If you want to do the force velocity balance work and profile, this would be based off when the thumb leaves the floor, and then it's out to 30 meters. So let's have a look at what this might look like. He's doing it from blocks. You don't need to do it from blocks. It can just be a 3-point start on the floor, or even a 4-point start on the floor without blocks. But obviously, if you're a track athlete, you must well combine the two. So that would be what a 30-meter acceleration would look like. Again, that timing has to be based off when an athlete first leaves the floor, and would have a little timing switch just under that thumb. If you do that force velocity profile, these are the type of numbers that you'll get back. So remember we talked about F0, this would be in newtons per kg, V0, velocity at zero force, what we might be expected to get if we don't have any weight, basically, and how fast we can run. Power max, watts per kg, force velocity slope, the RF max, the decline in the ratio of horizontal to vertical force, and the V opt, which is our last one down there, is how fast, this is actually my data, how fast I'd want to run if I was going to load myself up and use resisted sprinting, I'd want to set up something that makes me sprint at 4.15 meters per second. So I'd load myself up with a weight that would get me 4.15 meters per second over a 5 meter split. Just remember that practically. I might talk about that a little bit later. So we've got our details here. Velocity max from the test was about 7.93. The force I produced was 7.91 newtons per kg. VR was 8.29. Not bad for a 40-something-year-old. P max, 16.5 watts per kg. Force slope was -1. Ratio of force max, 44. DRF, the time and ratio of force, -8.9. Remember, we want that to be lower, the better. And then here we've got this 4.15. It's the velocity optimal. And this is what it looks like. We've got a power curve there in blue and our force velocity curve or velocity slope there in red. And this is based off the work of 17 and Meyer. Interesting enough, they do have recent work out that you can compare your slope to an optimal slope based on a few different measurements. A little bit of conjecture around that. At the moment, I haven't chosen to include this in the video, but if you are interested, I'll definitely recommend checking it out. Let's have a look at what some of the elite sprinters in the world might generate over the same test. So the guidelines for F0, like force at zero velocity, is around 10 to 11 newtons per kg, and power max about 20 to 30 watts per kg. Remember, I was about 16.5, so I'm a little bit below that, and my force zero was around 7.8 from memory. So again, a little bit below that. But you can see here these sprinters. So this is Su Bing 10 is the sprinter I was lucky enough to work with in China. 9.83. That was in the semi-final of Tokyo. Lamont Jacobs, who won the gold medal in Tokyo, 9.8. Fred Curley was did really well. Andre de Grasse, 9.89. He was a silver medalist in Rio. Bolt, this is Bolt's world record. Borzov, here's Elaine Thompson, 10.61. Shelley Fraser Price, 10.74, 10.71. Flojo, 10.54. And we can see all their 30 meter times through here. We can see their velocity at 30. Then we can see the F0, so force at zero velocity. And you see Sue's force at zero velocity is calculated very high based on the profile. But that's partly due to his weight being a little bit lower, maybe 70 kgs to 75 kgs, versus someone like Lamont Jacobs, 80 to 85 kgs. And then look at their V0. Now, one thing this model does is undercooks the velocity at zero force a little bit. For instance, Lamont Jacobs actually touched above 12 meters per second in that Olympic final, but the predicted V0 from his first 30 in that 9.8 only came in at 11.6. So it undercooks V0, and like anything, it's just a model, it's not perfect. So just be aware of that when you're working with this. Then we've got a power max, so very, very high power maxes through all of these. You can see 10.14, 29.0, but everything else above 30. The ratio of force max, again, the higher the better. Sue's got the best 60 meter and 100 meter history. So even though he didn't break the 100 meter world record, his 60 meter split is the fastest ever. And then you've got that decline in the ratio of force max, and you're looking at lower the better in acceleration. We've got all these numbers through here all around, basically in the 8s, except for Bolt 7.1, which is the world record for the guys at least. So these give you some comparisons if you are going to use the force velocity profile with what elite sprinters will look like. But the guidelines are generally force zero, 10 to 11 newtons per kg would be great. Power max, so the relative power watts per kg, 20 to 30 watts per kgs. And obviously the V0 above 10 meters per second would be what you'd be looking at if you're, above 11 meters per second if you're dealing with a elite sprint, above 10 meters per second if you're dealing with an outside back or striker in your field sports, maybe about 9 meters per second if you're dealing with like a middle forward in the NRL would be exceptional. So those would be the things you'd be looking at. Now, let's have a look at some of these. Just like what we did with the flight time, contact times, and maximal velocity, we can look at our stride lengths, our stride 1, stride 2, stride 3, stride lengths, relative stride lengths, flight times, and contact times. These are all based off, again, the biomechanics reports from World Athletics. And the big one, again, I'll point out is that relative stride length. Really like comparing it to an athlete's height, but you've got the 0.6, 0.7, 0.75. So stride lengths generally get longer and longer and longer. Flight times start getting a bit longer to correspond with that. Contact times start shortening little bit by little bit by little bit as you go through. So that gradual rise in center of mass, that gradual taking off like an airplane, will dictate flight times will increase a little bit, okay, and start pushing up to that 120 milliseconds type mark. Contact times, especially for lower level athletes, probably start around the 200 milliseconds and then start drifting down to the 100 milliseconds and potentially 90 to 80 milliseconds for the real fast elite guys. But that's your start. Your first three strides look something like that. 1.1 meters from the start line, 1.25, 1.4 from the front foot, and that's stride one. Okay, so we've looked at some of the stride length, flight times, contact times from a 60 meter sprint actually. This is some work from Liz Fellman and analysing the 40-yard dash for combine preparation. And this is what they'll consider world-class or elite in the 40-yard. So you see it's a little bit lower than what you might see into the stride length from elite sprinters. So striding to 1 meter to start, 1.05, 1.45 by the time you get to stride 3. The stride lengths of the elite sprinters, remember, if you can, were 1.1, 1.25, 1.4. Flight times are pretty similar. Contact times will be a bit longer. And again, they're getting down to what we're looking like closer and closer as they start getting to that stride 3 and pushing out from the acceleration. So these are comparisons for the 40-yard dash. You can use both numbers, both set of numbers, one for track sprinters and one for field sport athletes. And this will be set up from a 3-point start as the other key difference. So you've assessed acceleration, you've got your times, you've got your force velocity slope. Now you might want to do something called a load velocity profile. And this will give you a bit more tighter prescription for your resisted and weighted work, besides just relying on the 50% of the maximal sprinting speed or the V0 to determine what you're going to do. So you can do something like 25% body weight for 25 meters, 50% body weight for 20 meters, 75% body weight for 15 meters. In the past, I've just averaged those out between athletes in terms of, say if we've got an athlete that's 80 kgs and an athlete that's 70 kgs, we might do 20, 40, 60 kgs across both. One will be working a bit higher, but it'll come out where you compare relative to body weight and the times. And the times you're picking up are over 5 meter segments. The other thing I'd say is if an athlete is slowing down by the 20 with 25% body weight, you don't need to keep going to the 25. It's only where you get that from there. What you do from here, you plot the speeds they're getting at the relevant amount of body weight, and then that will determine how much weight you want to get to and where that 50% mark is in terms of actual maximum sprinting speed. So if I run at 10 meters per second, where whatever weight gets me 5 meters per second, that would be the way I'd look at and work with from there. And this is this load velocity profile, but I'll talk to you later on about what we can do with the load velocity profile in terms of setting up weights for speed strength, weights for strength speed. And really cool way of going about applying similar concepts that we'd use in the weight room to the field and resisted acceleration. Again, I've mentioned this, you can use that 50% of the maximum sprinting speed flying through your 10. That'll correspond with about your max power weight from cross settle. Now, this is done with a 1080 sprint device. The device name here is Legion Ju. He's a 847 long jumper, Chinese record holder actually. 4th place finisher in 2015 world champs in the long jump. Very, very talented individual, quite tall as well. And this is what a low velocity profile might look like with some resistance. So you can see there's a little belt on him and tag at the back, and that's getting pulled out from a 1080. And we'll just go through a whole spectrum of different loads from that 20, 25, 50, 75% of body weight, even up to 100% of body weight, depending on the athlete and how strong they are, how powerful they are. And essentially they'll do that with that resistance. Now, if you don't happen to have a 1080 Sprint or another resisted motorized device, you can also use plain old sleds. And there is actually some cool resources on the works from JB about using an exogeny as well, which some of you, if you're speed aficionados, you might know of the exogenies, which is basically a resisted rope device. But anyway, you can use sleds to do the same thing. In this video, he also holds the Chinese national record, 8:47 in the long jump. Wang Jianan, he's actually been a world champion since I've worked with him. He finished bronze medalist in the 2015 World Champs when he was 18, and very, very talented athlete. This, again, sprinting with the sled over certain distances at certain percentages of your weight will have to determine that low velocity profile. So let's have a look. So simple concepts and very, very applicable field tests. And I'll give you an understanding of how strong your athletes are in the specific task of sprinting. Because they might be very strong in the gym, but core accelerators with the sled in terms of moving it out and in terms of being able to really produce force horizontally. And you see it all the time, especially in taller athletes who have a hard time really accelerating forward. The resisted sprinting is a great option. For one, profile them, and then later on we'll talk about what you can do in terms of programming interventions.